Welcome to U7L5 Permutations and Combinations. In this lesson, we're going to talk about permutations and combinations, which are different ways of arranging or grouping items, and basically how many ways that can happen. First, before that, we're going to talk about what a factorial is, because we're going to use factorials throughout the definitions of permutations and combinations. So a factorial of a number, so let's call it n, is the product, so when you multiply them all together, of all natural numbers. Those are positive whole numbers from n down to 1. It's written as n with an exclamation mark and read as n factorial. The only factorial that breaks this rule is 0 factorial, which is in fact equal to 1. Similar to a value to the 0 power is also equal to 1. We're going to evaluate each expression for example 1. So these numbers can get really big really quickly, so I do recommend using a calculator to make this go more quickly. But basically we're going to evaluate these. So 6 factorial is the product of 6 times every whole number smaller than 6 all the way down to 1. So this is equal to 6 times 5 times 4 times 3 times 2 times 1. So you multiply all those numbers together and you will get the value. So 6 times 5 times 4 times 3 times 2 times 1. And that's going to be 720. So the expression 6 factorial is equal to 720. Let's do the same for 13 factorial. Hopefully you realize that 13 factorial is in fact going to be much larger than 6 factorial, because we're going to do the same thing, except we're going to start with 13 and multiply all the way down to 1. So 13 times 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now I will go ahead and point out that we already did 6 factorial, okay, which is this part, 6 times 5 times 4 all the way down to 1. So we already know that that part's equal to 720. So if you want, you can actually just exchange that for the 720, okay, from A, and then you can go ahead and go from there. So we can multiply 13 times 12 times 11 times 10 times 9 times 8 times 7 times, and instead of doing all those numbers again, we already know it's 720 from part A, and we're going to multiply that. So that's going to be a big number. So it's 622702080, which if I put my commas in, we can see is over 6 billion. All right, I'm going to show you a little trick here to simplify C and D quicker. So we have 18 factorial over 10 factorial. So the factorial that's going to have more values is the bigger number, like 18, right? 18 factorial is going to have more values that we're multiplying. So I'm going to start there. But once I get to the point where I have the same number as I have in the denominator in the smaller factorial, I'm actually going to show you a little trick here. So I'm going to start with 18 times 17 times 16 times 15, keep going till I get to 10. 14 times 13, 12, 11, 10. So instead of doing 10, 9, 8, I'm just going to leave the 10 as the factorial, because I know it's going to keep going with 10, 9, 8, etc. And then I'm going to put the 10 factorial back in the denominator. Now, if I'm multiplying by 10 factorial and dividing by 10 factorial, I can basically get rid of them. 10 divided by 10 is 1. And what I'm left with is 18 times 17, etc. So I'm just going to multiply all of these, and then I should get my simplified answer here. So 18 times 17, I'm doing this in the calculator, times 16 times 15 times 14 times 13 times 12 times 11. And that's going to be 17643222560. Again, I believe that's over 1 billion. Let's do it one more time. So we have 7 factorial, 9 factorial. I'm going to start with the bigger factorial. So I'm going to leave 7 factorial as it is. I'm going to start with the bigger factorial. So 9 times 8 times, now I'm at 7. So I'm going to leave that as a factorial. Again, I'm multiplying and dividing by the same factorial. So that becomes 1. So I'll just leave 1 on top. And that's going to be 1 over 9 times 8, which is 72. And we'll go ahead and leave it that way. All right, moving on. So a permutation. So a permutation is an arrangement or lineup of objects in which the order matters. So we're going to figure out how many ways we can line up objects when the order matters. Okay, so that's what a permutation is going to give me, an arrangement or a lineup, and it's going to tell us how many ways that can occur if the order matters. Okay, so for example, when you're finishing a race, everyone can be labeled with the place that they take, first, second, third, etc. when they cross the finish line, excuse me. So the order matters. Think about a word, right? If I talk about the different letters that are in a word, the order that I write the letters in matters, right? Because it's not going to make the same word if I change the letters around. Things like that, okay? All right, so there's a formula for permutations. And the formula has an N and then a capital P and then an R. Notice that the N and R are actually subscripts. And then the formula says n factorial over n minus r factorial. So let's talk about what that really means. So n is the total number of objects to choose from. Usually the objects can be, it can be actual objects, like books, things like that. Sometimes it can be like letters in a word. It can be people. It can be numbers in like a password, things like that, okay? So n is the total. That's the total number of objects. R is the number of objects that's being used for that arrangement. Okay, so R is basically the ones that we're actually choosing for that arrangement. Now, we can choose all the objects for the arrangement. Many times we don't, but we could choose all the objects as well. So there isn't a possibility that R and N are the same value, but oftentimes R is actually smaller than N. Okay, so just keep in mind that R has to be less than or equal to N. It can't be greater because the R is the amount that we're actually choosing. It's the number of objects that we're using for that arrangement. So it can't be more than the objects we have available to use. Okay. All right. And then based on that, just keep in mind that what this, actually, let me move this real quick down here. Okay, guys. So what the top number is the total. So that's the total factorial. And the bottom number is N minus R, which is the difference factorial. Okay. It's the difference of the two factorial. So the difference of the two factorial. Now an important shortcut, okay, because if n is r, then the difference is going to be 0. And 0 factorial is going to equal 1 like we talked about above, right? So that means that if you end up using the exact amount that you have available, it's just that number factorial. It's just the total factorial. All right, moving on. So for this next group of questions, for example 2, we're going to represent each problem as a permutation and then evaluate. As we go, I'm going to try to point out why it's a permutation so that in the future when you see them, you can identify whether it is a permutation or what we're about to learn about, which is a combination. Okay, so A, how many ways can the letters in the word education be arranged? So basically think about this. First of all, there's 1, 2, 3, 4, 5, 6, 7, 8. There's 9 total. So n is 9. Okay, actually, before we do this, let's go ahead and write the formula at the top just so we have it here. So remember, n is the total. Okay, r is the ones you're choosing. Okay, so the ones you're choosing for the arrangement. And then our formula is a subscript n, capital P, subscript r. And that formula is the total factorial, so n factorial, over the difference n minus r factorial. Okay. Perfect. Okay, so we have our total of 9. Now, how many ways can we arrange the letters? Well, each letter has a position, right? The first letter in the word, the second letter in the word, the third letter in the word, and so on and so forth. So every single one of these positions has an order to it, right? First, second, third, etc., all the way to the 9th. And so that's why it's a permutation, right? Because if I put a different letter in the front where E is right now, then that is going to be different than leaving the E there, right? So the order does matter. Okay, perfect. So we have N is 9, but we're going to rearrange all the letters. So that means R is also 9. We're actually going to arrange all of them that we have available. Okay, so our shortcut tells us that if that's the case, if we're doing 9 permutation 9, we're just going to go with that number factorial. So 9 factorial. Now, if you remember, on the front, we actually did 6 factorial. So 6 factorial is going to help us here because we can do 9 times 8 times 7 times 6. And we can go all the way down to 1. But because we did 6 factorial on the front, because we did that, we can actually take that value of 720 and we can multiply 7, 8, and 9 to it. So 720 times 7 times 8 times 9. And we get 362,880. Okay, possibility. So that's all the possible ways that we can arrange the words or the word education, the letters in the word education, if the order matters where we put them. All right, perfect. Let's look at another one. How many ways can Emma arrange 7 books on a shelf? Okay, so she has one shelf and she's arranging the 7 books. Now, You wouldn't necessarily say this is the first book, this is the second book, like in terms of one being better than the other. You could. But in this case, the arrangement matters because on the shelf, you can say this one is on the left, this one is on the right, this one's in the middle, right? This one is to the right of the very left book, that kind of thing. So they all have a position. They all have a specific position, which is basically the same as having an order to it. Okay, now the total that we have to choose from is 7, so N is 7, but we're arranging all the books, so R is also 7. We're arranging all those books, so R is also 7. So it's 7 permutation 7, and that's 7 factorial, which again is 6 factorial is going to help us because it's 7 times basically 6 factorial, right? 6, 5, 4, 3, 2, 1. So it's going to be 720 times 7, which is going to give us 5040. 5,040. Okay, so that's all the possible ways that we can arrange those 7 books. Okay, how many ways can the letters in the word bottle be arranged if the first letter must be B? So the first letter is B. That means I cannot move this B. It is stuck there. It is stationary. There's nothing I can do to change it. So we can basically ignore it because I cannot change where that B is. Okay, I cannot change where that B is. I can only change O, T, T, L, E. So I can only change 5. So N is 5. That's the total possible letters that I can rearrange. And the order matters just like it did when we talked about education, right? So it's a permutation. And we're still arranging all 5 of those. So R is also 5. Okay? So again, the shortcut for this, 5 permutation 5, is just 5 factorial, which is just 5 times 4 times 3 times 2 times 1. And that is equal to 120. Perfect. Now let's look at the next one. There are 10 dogs in a dog show. How many ways can they be awarded first, second, and third place? Perfect. So there's 10 dogs in a dog show. That's the total. That's N. N is 10. How many ways can they be awarded first, second, and third place? So first, second, and third place. The order of those matters, right? First place is different than second place, which is different than third place. It's not like saying we just have 3 dogs that are the winners, right? And they're all equal. No, there's a different level to each of those. So this is a permutation. Now R is not 10 this time because we're only choosing 3, first, second, and third. So R is 3. So now we start with the total of 10. We do the permutation on just 3 of those items. Okay, so since we're only choosing 3 of those items, this number shouldn't be quite as big as it would have been if we were choosing, for example, all 10, right? So this is now going to be the total factorial, so 10 factorial, over the difference, so 10 minus 3 factorial, which is going to be 10 factorial over 7 factorial. If we use the hack that I showed you guys for the beginning of the notes, we can write the bigger factorial, which is the top number, 10 factorial, all the way, we can start writing the factorial, right? 10 times 9 times 8 until we get to 7 factorial, and then we can basically cancel them out. So 10 times 9 times 8 times 7 factorial over 7 factorial. And so now, basically 7 factorial and 7 factorial cancels, and you just multiply 10 times 9 times 8. So 10 times 9 times 8, which gives us 720. So that's going to be 720. All right, let's look at the next one. It says if there are 16 players on a hockey team, how many ways can the coach choose a captain and an assistant captain? So, first of all, the total, right? N is 16. There's 16 players. The coach is choosing a captain and an assistant captain. So these 2 people that he's choosing, or she's choosing, whatever the case is, the order matters. A captain and an assistant captain have different roles, right? There's a different name for it. It's not just 2 people to lead the team, right? It's 2 specific people, and the order matters. So it's the R is going to be 2, and this is going to be a permutation. So we're starting with 16 players, and we're going to permute, right? We're going to do a permutation for 2 of those players. So it's going to be the total factorial, 16 factorial, over the difference of 16 minus 2 factorial. So that's 16 factorial over 16 minus 2, which is 14 factorial. Using our trick again, we have 16 times 15 times 14 factorial over 14 factorial, right? And so 14 and 14, they basically cancel, and then we just have to do 16 times 15. And you get 240 ways in which 2 people, the captain and the assistant captain, can be chosen. All right, let's take a look at these last 2. So the next one, it says a homeowners association has 12 board members. How many ways can president, vice president, and treasurer be chosen? So 12 board members. We're choosing president, vice president, and treasurer. Okay, I'll do this. President, vice president, and treasurer. So the total is 12 for all the board members. And then we're using a sample, right? Or we're choosing 3 of them. Okay, president, vice president, treasurer. Now this is a permutation again, because president, vice president, and treasurer all hold different roles. They have a different title. It's not just choosing 3 random people to be the leaders, for example. So now it's going to be 12 permutation 3. So it's going to be 12 factorial over 12 minus 3. So 9 factorial, the difference factorial. So that's going to be 12 times 11 times 10 times 9. Now, because it matches the bottom, I'm going to leave that as a factorial. And then again, we're going to basically cancel those out. So I'm just doing 12 times 11 times 10. And that's going to be 1320. Last but not least, it says using the digits 0 to 9, how many ways can Sarah create a 5-digit password if there are no repeating numbers? Okay, so the digits from 0 to 9 is going to give us our total. So that's 10 numbers. It says, how many ways can Sarah create a 5-digit password if there are no repeating numbers? So no repeating numbers is important, because if we could repeat a number, then when I use, for example, 7, I could use 7 again. And so it's not really rearranging them. It's a little bit different, okay? But since I can't repeat any numbers, it's just rearranging them. And she's creating this 5-digit password, okay? So every single number in this password, the order matters, right? Because if I put this first digit here in my password and then I were to move it to say the last digit, now my password's not going to work, right? That's how passwords are made to work, right? The place that you have that digit matters. So the order matters. So it's definitely a permutation. Since we're choosing 5 digits, the R is 5. Okay, so let's take a look. So we have 10 permutation 5. And that's going to be 10 factorial over 10 minus 5, which is 5 factorial. That's going to be 10 times 9 times 8 times 7 times 6 times 5. I'll leave it as the factorial, so it now, because it now matches the denominator. And then 5 factorial in the denominator. 5 factorial over 5 factorial is 1. We don't need it anymore. So now just multiply everything else. 10 times 9 times 8 times 7 times 6. So 90 times 8 times 7 times 6 is going to be 30,240. Okay, 30,240. All right, now let's look at this last part of the notes. Now we have a combination. Let's take a look. It says a combination is a grouping of objects in which the order does not matter. Okay, so for example, when choosing 4 representatives to attend a meeting in a class of 20, the order they are chosen in does not matter. So if I just say, okay, here's 4 representatives, they don't have any special title, I just need to pick 4 students, then if I choose, let's say I choose Adam, John, Mary, and Sam, right? Those are my 4 representatives. I can change that order all I want. It doesn't change the 4 representatives that are attending the meeting, right? I can change the order to John, Adam, Sam, and Mary. And guess what? It's the same 4 students, because it's just 4 people going to some meeting. Ooh, can't spell John. Okay? And so the order does not matter when it comes to something like that. The order does not matter. Okay? So the order they're chosen in does not matter. So the combination formula is a little bit different. There's going to be less choices here for combinations because the order doesn't matter, right? These are counted as the same with the combination. So the formula still starts with the total factorial, but in the denominator, instead of just doing the difference factorial, you also multiply it by the one that you chose, right? The chosen factorial. So in the bottom, you're dividing more than you did before, and that's what's going to make that number smaller, okay? An important shortcut is if you have a total and you're going to use a combination of that total, that's just going to be 1, okay? That's going to end up just being 1. There's only one way to choose everybody in the class, right? There's only one way to do that. Okay, so let's take a look at these. Represent each problem as a combination and then evaluate. Okay, so remember, N and R still stand for the same thing. It's just now these are going to be combinations where the order doesn't matter, and we'll talk about why that is. And so that's going to change the answer. So there are 12 math teachers at a school. In how many ways can all 12 of them be chosen to attend a conference? So there's 12 math teachers to begin with, so N equals 12. Okay, now the ones I'm choosing is all 12 of them. So I'm choosing all 12 of them. So the shortcut that is right here above says that if I do that, if I do 12 and I do a combination of all 12, I'm for sure going to get 1. But I want you to see why that makes sense. So let's plug it into the formula. So we have n factorial, so the total factorial, over r factorial, which is 12 factorial, because r is 12. And then we have 12 minus 12 factorial. Okay, we end up with 12 factorial over 12 factorial times 0 factorial, which is just 1. So 12 divided by 12 ends up just being 1. So we're choosing all of them. Now, the reason, again, why this is a combination, if I didn't already say this, is because the order doesn't matter, right? There's just 12 math teachers. We're choosing all 12 of them to go to a conference. There's no order to it. They don't have any labels. They're not sitting in a specific spot. We're just choosing them to be grouped together. So I think of combinations as more of a grouping, of a put everybody in just like a little pile, right? Everything, every object in a little pile versus putting them in a lineup, okay? All right, let's look at this next one. Okay, let's look at this next one. So this next one says, how many ways can 4 cards be chosen from a standard deck of 52 cards? Again, we're choosing 4 cards, possibly using them for, I don't know, some trick or whatever the case is. But there's 4 cards chosen in no particular order. They're not going to be set in a particular order. So this is a combination where the total is the 52 cards in the deck. Okay, and the R, the one that you're choosing, is the 4 cards out of the deck. So it's going to be 52 combination 4. So that's going to be your total factorial over, okay, your R, so 4 factorial, times the difference, 52 minus 4 factorial. Okay, so be very careful here. So we have 52 factorial over 4 factorial times 52 minus 4, which is 48 factorial. So we can still use our little trick, except we have that extra 4 factorial there. So don't forget about that. Okay, so what we're going to have is 52 times 51 times 50. Actually, hold on, I'm going to run out of room. Let me write this below. So this is going to be 52 times 51 times 50 times 49 times 48, all over, 48 factorial, over 4 factorial, which is 4 times 3 times 2 times 1, times 48 factorial. Okay, so again, what did I do? I changed the 52 factorial. I multiplied all the way down until I got to the 48 factorial so that it would match the bottom, right? That number in the denominator. Now I can go ahead and cancel those. And I'm going to end up with, so you got to be careful here. There's a little more simplifying to do. 52 times 51 times 50 times 49. And you can simplify this before you do this part. But I just want to go ahead and show you what happens. 6497400 over 4 times 3 times 2 times 1. So 4 times 3 is 12, times 2 is 24, times 1 is still 24. And of course, we can simplify this. I'm going to go ahead and use the calculator to simplify it. So alpha and the one next to alpha, 6497400 over 24. Oh, actually, it divides evenly. Perfect. So it actually divides evenly. And so that's going to be 270725. Okay, so those are all the possible ways that we can choose 4 cards if the order doesn't matter. All right, next. So it says there are 33 students on a class roster. How many ways can the class choose 5 students to clean up the room? So there's 33 students on the roster total. How many ways can the class choose 5 students to clean up? So the order doesn't matter, right? There's just 5 students in a group cleaning up. So our total is 33, and the ones we're choosing are 5. So it's going to be 33 combination 5, and we're going to use our formula. So that's going to be the total factorial, so 33 factorial, over the chosen factorial, and then the difference factorial. Okay, so that's going to be 33 factorial over 5 factorial times the difference, 28 factorial. And again, we can use our little trick. So we're going to end up with 33 times 32 times 31 times 30 times 29 times 28 factorial over 5 times 4 times 3 times 2 times 1 times that 28 factorial. Okay, so we end up crossing out our 28 factorials. That equals 1. And then we go ahead and multiply, and then on top and bottom, and then we can divide. Hopefully it divides nicely. So 33 times 32 times 31 times 30 times 29. So that's going to give us 284,80320 over, I believe this is 120. We did this earlier. 5 times 4 times 3 times 2 times 1 is 120. If we divide those, we do get a whole number. So we get 237 336 ways that you can choose 5 students to clean up the room out of 33 students. Okay, a couple more. A grocery store is hiring 2 new employees. There are 18 applications. How many ways can they choose to? So they're choosing 2 new employees. It doesn't say anything about the order, right? No one's going to be making more money or anything like that. So a grocery store is hiring 2 new employees, and there's 18 applications. So the total is 18, and then they're going to be choosing 2. So 18 combination 2 is going to be the total factorial over the chosen factorial times the difference factorial. Okay, so that's going to be 18 factorial over 2 factorial times 16 factorial. And then it's 18 times 17 times the 16 factorial over 2 times 1, basically, right? Which is just 2 times 16 factorial. So if we simplify, we end up with just 18 times 17, 18 times 17, which is 306 over 2. And when we divide that, we end up getting 153. So 153 ways that they can choose 2 people out of the 18 applications. All right, last one. Ellis can omit any 5 questions on his 30-question math test. How many ways can he choose the questions he wishes to omit? So he can omit any 5 questions, and he has 30 questions on his math test in total. So his total number, N, is 30, okay? And his R is going to be 5, because those are the ones that he's choosing to omit, right? And so he's omitting random 5 questions. There's no order to that, so that's going to be combination. So it's going to be 30 combination 5, which is the total factorial, 30 factorial, N factorial, right? Over the chosen, which is 5 factorial, which is the R, times the difference. So 30 minus 5 factorial. So that's going to be 30 factorial over 5 factorial times 25 factorial. And again, we use our little trick. So we end up with 30 times 29 times 28 times 27 times 26 times 25 factorial. Again, I'm leaving that one as a factorial because that's what I have on the bottom in the denominator. And then over 5 factorial times 25 factorial. So if we simplify a little bit here, then we end up getting... So the numbers on top, I'm going to go ahead and multiply those. And on the bottom, I know it's 120 because I've done that a few times in these notes already. So 30, 29, 28, 27, 26. If I multiply those, I get 171,00720. Denominator is 120. Divide. And I'm going to get the total possibilities here, 142506. 142506 options there. All right, thanks for watching these notes, everybody. Have a good day.